Gentlemen, boys and girls, hello and welcome. My name is Mark Hatfield. It's the 4th of September 2024. Today I'm going to be talking about a basic framework of fundamental principles for the universe. Now, before we start, I just want to talk a little bit about the Einstein effect. So the Einstein effect, one of the best examples of this is probably the water jug experiment in 1942. In this experiment, they took two groups of people and they gave them 5 questions. They're all water jug questions where you were given 3 different volumes of water jug and you had to come up with a final volume from those 3 jugs. So an example of this would be if you had a 10-litre jug, a 4-litre jug and a 1-litre jug and you need 17 litres, then you could take the 10-litre jug, add 2 of the 4-litre jugs and then take away 1 of the 1-litre jugs and you'd end up with 17 litres. So of these 2 groups, the first group was just given 5 questions with no preparation, and they did all 5 questions very well without any problems. The second group was given the exact same 5 questions, but the second group was given 5 prep questions to practice with. Now, these prep questions were all different questions with different volumed water jugs and different answers, but the solution to all 5 of these prep questions was exactly the same. And that solution was that you could take 1 of jug A, 2 of jug B, and take away 1 of jug C, and you would end up with the correct solution every time for each of the 5 questions. When the second group of people did the same 5 questions as the first group, the first question could be answered with the same solution, A plus 2B minus C, and you'd get the correct answer. The second question could also be answered, A plus 2B minus C, but also had a much simpler, easier solution, which was just you could take 2A, and that would give you the same answer. All the people in the first group that didn't have prep, they used this simple way to answer by answering with 2A. All the people in the second group that had been given the 5 previous questions or the same solution used the more complex and difficult solution to solve the problem, the same way they'd solved it 5 times earlier. The third, fourth, and fifth question, however, could all be simply solved, but none of them could be solved with the solution A plus 2B minus C. The first group had no problem answering the third, fourth, and fifth question, but the second group that had 5 practice questions prior and already answered the previous 7 questions with the same solution were unable to solve these water jug puzzles. They had a fixed solution for how to solve this problem, and they were unable to think of original ideas to solve these problems in a different way. And so they really struggled and could not answer the third, fourth, and fifth question. And even when the supervisors prompted them or gave them the solution to the problem, there was often disbelief and frustration that resulted in emotional outbursts like saying this test was stupid or the examiners were dumb. So why am I telling you about the Einstein effect? Well, it can be very hard to unlearn something that you already know. It can often prevent you from finding a better solution and can often result in the loss of reasoning and emotional response. So even when the correct answer is given, there is still disbelief as it contradicts your current beliefs in how to solve a problem. This becomes very relevant when I talk about physics because many of you already have current beliefs and have heard other alternative theories for many of the problems I'm going to talk about today. And so even if I present a logical and reasonable argument, there will naturally be an Einstein effect where there's disbelief or because there is already a solution known for many of these problems. So why am I telling you all this? Well, I want to make it very clear. I'm not a physicist. I am just a guy who wants to express how I see something from an outside perspective. I'm not looking for a debate or an argument or conflict. If you do find yourself getting frustrated, then that's normal. But try to recognize that and consider, is this the Einstein effect? So I want you to know that I know what you already know, and that is that I acknowledge that I'm not a physicist. I know I am not an expert, and I know that you probably know a lot more than I already know already. So, what am I going to talk about? I'm going to present broad topics which you already know in immense detail in a simplistic way from an outside perspective in an attempt for you to consider things that you already know in a different way. I want to present a way of connecting everything you already know into a simple framework of fundamental principles in an attempt to see the big picture. So let's go back to basics. When we look at a complex topic, there is often a set of fundamental principles that we can use as a baseline to help us better understand and connect more complex topics. One example of this is in the science of biology. So Charles Darwin came up with a theory of evolution, which basically created a set of fundamental principles in which we could understand all life on Earth, alive and dead. Using these basic fundamental principles, we can come up with a simple diagram, like the tree of life, which is made up of basic fundamental principles and can be displayed on a single page, and yet can explain an immensely complex and detailed topic like all life on Earth, alive and dead. Another example is in chemistry, where we can take simple fundamental principles like the structure of an atom, and we can use this to create a chart of all the known elements, and we can display this in a simple, easy to understand table which can fit onto a single page. And from these basic fundamental principles, we can explain everything in chemistry, from how to make dynamite to the structure of the human genome and all enzymes in the human cell. What about physics? We want a simple set of fundamental principles that can help us explain the universe and the phenomena that we. Everything that I talk about today, every theory, every phenomenon that we observe, every idea that we have, and everything that I'm going to talk about comes down to a single fundamental premise, that space is a medium. I believe that space is a medium of particles which has properties similar to a gas. We can think of space in our universe in a similar way to the air in our atmosphere. Using a single fundamental premise that space is a medium, I want to explain every observable phenomena in the universe. I've broken this up into several categories, so I want to talk about the universe, how the mass is distributed through the universe, and how that mass distribution changes over time. I want to talk about the cosmic web. I want to talk about gravity, again, using simple fundamental principles so that we can understand what gravity is and how it works, not just on a quantum level or a classical level or a relativistic level, but on all levels through a simple, easy to understand first principles. I want to talk about dark matter and the properties or phenomena that we observe, the evidence for dark matter, like the cosmic web, cosmic microwave background radiation, galaxy clusters and collisions, the galaxy rotation curve, gravitational lensing, and other properties that make us believe in the existence of dark matter. I want to talk about why the universe is expanding, why the expansion is accelerating at an accelerating rate, and what dark energy is. And I want to talk about other things like quantum mechanics, electromagnetic waves, and relativistic effects. And I want to do it all with the same fundamental principles which connects all of them together. So I want to make this clear. I want to discuss multiple points in under an hour. Every point already has a current isolated explanation or theory. You may not agree with many or all of my explanations, but I only have 1 to 2 minutes to explain each point. I don't have time to discuss each point in detail. I don't have time to discuss current theories like relativity. And the big take-home message here is that no other theory explains all these points in a single theory. So this talk today is going to quickly cover these topics. We're going to talk about gravity, stable orbits, galaxy formations, galaxy clusters and classical Newtonian gravity, galaxy rotation curves, the mass distribution of the universe over time, and dark matter. After I've talked about these general theories, I will then talk about some basic maths to help support these theories. I do not have time to discuss everything, and just because I don't talk about it does not mean that I have not thought about it. So let's start with gravity. When we think of gravity, we think of the theory of relativity. We think about the space-time and how mass curves space-time. We think about how that curvature of space-time alters the path of objects traveling through space-time, and this results in the effects that we observe as gravity. Now, I know many physicists do not like this analogy because it oversimplifies the theory of relativity, and there's multiple problems with it. However, I'm going to use it as an example because it helps me illustrate a single point. So if we imagine the curvature of space-time like a bathroom sink, then we can imagine the drain in the center of that sink as a central mass like the sun. We can think of the sink around that drain as the curvature of space-time. And if we throw objects like marbles or balls into that sink randomly, some of those balls will bounce out of the sink and escape the sun's gravitational orbit. Some of those marbles will fall directly down the drain and be consumed by the central sun. Some of those marbles will crash and collide and bounce around, but eventually one or two of those marbles will form a stable orbit around the drain and orbit the sun. This makes me think, what are the chances? What are the chances that an object traveling through space-time would form a stable orbit around a larger central mass? Let's take the Earth orbiting the Sun, for example. In order for the Earth to orbit the Sun in a stable orbit, it must have a perfectly predefined set of orbital parameters in order to orbit the Sun. It must be in the right location, traveling in the right direction, at the right velocity, at the right time, in order for it to orbit the Sun perfectly in a stable orbit. If our Earth was closer or further away, if it was moving slightly to the left or slightly to the right, if it was moving faster or slower, or if it was slightly out in time, then those orbital dynamics would not be precise enough for the Earth to form a stable orbit. So what are the chances of that happening? I would argue that it's less than 100%. Let's imagine it's 1 in 10. So 10 objects fly past the Sun, 9 of them either get consumed by the Sun or escape its gravitational field, but luckily enough, one of those 10 ends up orbiting the Sun, like the Earth. If we say it's a 1 in 10 chance, then we must add each additional object that is orbiting the Sun to that calculation. And so with every additional object, the chances of these objects forming a stable orbit. Let's extrapolate this problem out to galaxies. A galaxy is made up of up to 100 million stars. Every single star in that galaxy must have precise orbital dynamics in order for it to orbit that galaxy. Every single star has to have the right distance, the right velocity, the right angle and projection at the right time for that unique individual star and its relative location to that galaxy. And if any of those parameters are out, then that star would not orbit that galaxy. This has to happen every single star in that galaxy. With every additional star in that galaxy, the chances of this happening are less. If we believe that every star in that galaxy has its own unique, precise orbital dynamics for that individual star in that individual location, then what happens when we add mass to that galaxy? When that galaxy collides with another, then the precise orbital dynamics of each star is then altered due to the new mass and new gravitational force of that galaxy. We would expect orbital collapse and orbital chaos as galaxies collided. Our current understanding of gravity is great for telling us exactly the properties of any object orbiting in a given orbit. That is because to be in an orbit, it must fit a perfect set of variables which we can easily calculate. But our current understanding of gravity does not explain how every object got into that orbit in the first place. Theoretically, it is statistically improbable that we would observe galaxies in stable orbits. Yet in nature, it is common to see stable orbits and uncommon to see orbital chaos or collapse. This leaves me with these questions. How did an orbiting object get to be traveling at the exact right direction, velocity, and distance at the exact right time for it to enter a stable orbit? How does it explain galaxy formations and collisions? Why do stable orbits naturally form in nature? Aren't these statistically improbable? Why are they so resilient? Using our analogy of the bathroom sink, it is difficult for us to answer these questions. However, if we change one parameter in this analogy, then all those questions become much simpler and more intuitive to answer. Instead of having objects traveling through space-time and being caught in warped space-time around large masses like the sun, we could fill our bathroom sink with water. If we filled our bathroom sink with water, and then we threw our objects or balls into the sink, then those objects would land randomly wherever they landed, and they would sit motionless, floating in water. If we pulled the plug out of the drain, the water would be consumed by the drain and sucked down through the plug hole. As the water was sucked into the plug, the surrounding water in the sink would form a vortex and start to orbit around the drain. Any objects floating in that water would naturally move with the moving water as it was sucked into the drain. We would see all objects move in the same direction at the precise right velocity for its location relative to the drain. It wouldn't matter where the objects were or how many objects were in the sink. All of the objects in the sink would begin to orbit the drain. We could take this analogy and compare it to space in our universe. If we imagine that space was a medium like the water in the sink, and we imagine that mass consumes space like the drain consumes water, then we could imagine that as water is sucked down the drain, that it would begin to orbit that central drain. We could also imagine that if space was being consumed by central mass, that space would be drawn in and begin to orbit around that central mass. Any objects floating in water or any objects floating in space would naturally move around that central mass as the space was consumed. We would expect any object in any given location to orbit at the precise orbital dynamics expected for its location given to the center of the mass. If we added more objects, they would also form their own orbital dynamics depending on their location. Regardless of how many objects there were or where they were placed, they would all orbit in their own unique orbital dynamics given the location that they lay in space, just like balls scattered through water as it goes down the drain. Here's a video of water being sucked down the drain. Using this analogy, we can imagine that space is like the water in the sink, that mass is like the central drain consuming space, and we can see that as the water is consumed by the drain, it is sucked down and begins to orbit. It forms a vortex around the central object. We can imagine space as being consumed by a central mass and also being sucked around and beginning to orbit the central mass. Any objects that we place randomly through space or into the water naturally move with the moving water. They all orbit the central drain given their location in the water. If the object is closer to the central drain, it'll orbit faster. If it is further away, it'll orbit slower. It doesn't matter where the objects lay or how many objects there are. They will all naturally orbit the drain with perfect orbital dynamics. We can imagine our solar system or our galaxy in the same way. The objects, like balls or stars, floating in that space will naturally orbit the central mass as that central mass consumes the space that those objects are floating in. We can now take our analogy of the bathroom sink as an example of general relativity, and we can alter that analogy with one parameter to make a new theory that space is a medium like the water in the sink, that mass consumes space like the drain in the center, that objects orbiting the central mass are floating motionless in space as the space is consumed and orbits that mass. Therefore, we can make a hypothesis. Hypothesis 1. Space is a medium of particles which has properties similar to a gas. Hypothesis 2. Most objects in space are suspended, motionless in moving space. We can think of this like balls suspended motionless in moving water. To this, we could wonder what it would be like for an object to move through space. If we imagined an object like a boat moving through water, then that boat would displace the water in front of it, causing a bow shock. That displaced water would form jets and streams, which would then redistribute behind the boat to form a tail with turbulence and eddy currents. If we imagined what an object moving through space would look like, then we can use Mira, a variable star in our galaxy, as an example of what we might imagine if we saw an object moving through space. Just like a boat moving through water, Mira has a bow shock in front of it where it's displacing the gas as it moves through space. It has streams for that displaced gas, a tail, and eddy currents and turbulence coming off the back. Therefore, this star, Mira, would be a good example of what we might imagine a star to look like if it was moving through space. In contrast to Mira, our star, the Sun, is moving at a similar speed than Mira. Our Sun is orbiting in our galaxy in the same direction as all our other surrounding stars. Our star does not have a bow shock, streams, a tail, or turbulence off the side. Yet Mira, which is moving at a similar speed to our star in the galaxy, is not moving with its other surrounding stars. Hypothesis 3. Mass is constantly consuming space, just like a drain is constantly consuming water. Hypothesis 4. The effects of gravity are the results of the movement of space. If we look at the sink analogy and water going down the drain, we can see that that water is constantly moving in the absence of anything floating in it. If we imagine space like the water in the sink, we can imagine that space is constantly being consumed by mass and is constantly moving. When we put objects into that water, we can see the movement of that water through the objects floating in that water. Therefore, if we imagine that space is constantly moving, and we place objects in that space, like the planets in our solar system or the stars in a galaxy, then we can see the movement of that space through the movement of those objects floating in space. Therefore, we can say the effects of gravity are the results of the movement of space. Mass is how we visualize the movement of space, and mass is how we visualize the effects of gravity. This leads us to hypothesis 5. Gravitational acceleration is equal to the velocity and direction of space at any given point. And I'm going to use this hypothesis to formulate our mathematical equations to help us test against real-world data. Gravity is the movement of space. Now, this is a strange concept to grasp at first because it's counterintuitive to what we already know. So I'm going to say it again. Gravity is the movement of space. My definition of gravity does not mention mass. The movement of space, gravity, can be independent of mass. Mass is how we visualize the movement of space, and mass is how we see the effects. If we think of space as a medium, then we can think of space as a medium in the same way as we think of air in our atmosphere, or in the same way that we think of water in our oceans. If we think of gravity as the movement of space, and we think of space like a medium, like the water in a whirlpool, then we can see that the water in a whirlpool is moving in the absence of anything floating in it. If we placed a ball in the water, it would orbit naturally for its location, and we would see the effects of the moving water. We would see the effects of gravity. If we think of this in space, we can say that space is constantly moving, whether or not we can see it. We only see the movement of space when we see the objects floating in that space, and we see the effects of gravity by the movement of that space. We can think of space as a medium in the same way we think of air in the atmosphere. We can't see the air, but we can see the movement of the air through clouds floating in that air. We can't see space, but we can see the movement of space as the effects of gravity and the movement of mass floating in that space. If we think of space as a medium, then we can think of space in a galaxy like the air in a cyclone. We can think of galaxies as moving space, with mass floating in that space, similar to how we think of a cyclone as moving air, with clouds floating in that air. If we think of space as a medium like water, then we can think of galaxies as the flow of space, like the flow of water in a whirlpool. We can then think of galaxies as moving space with mass floating in that space, in the same way we think of a whirlpool as moving water with balls floating in that water. Space is a medium, then this accounts for the natural formation of stable orbits for almost every observable object in the universe. If space is a medium, then this gives us a logical explanation for gravity, which accounts for galaxy formation. We can now think of galaxies as moving space, like we think of water in a whirlpool. Any objects moving or floating in that space will naturally orbit those galaxies as the central mass of that galaxy consumes the space around it. If space is a medium, then we can think of galaxies as flowing currents in space, like a whirlpool. If we think of how flowing water moves in a river, or how two streams merge, we can compare this to galaxy clusters and collisions. As flowing water merges, it creates turbulence and eddy currents, but quickly converges to form a new equilibrium. If we think of galaxies as flowing space, then we could imagine that when they converge, this could cause turbulence and eddy currents before reaching a new equilibrium. In a similar way to how water would merge, we could use our knowledge of fluid dynamics to better understand galaxy clusters and collisions. If we think of space as a medium, then we can think of space like the air in our atmosphere. We could think of galaxies like cyclones. We could imagine galaxy clusters and collisions to be comparable to cyclones merging. We can see two smaller cyclones begin to orbit each other and merge to form a larger cyclone, in the same way that we could see two smaller galaxies begin to orbit and merge to form a new equilibrium. If we think of space as a medium, then we can think of our space like the water in our oceans. We can think of gravity as the flow of space, like we think of the flow of currents in our oceans. We could think of the cosmic web like currents of flowing space in our universe. If space is a medium, then we can think of space like the air in our atmosphere. We can think of gravity as the flow of space, and we can compare the cosmic web to jet streams or air currents in our air and the atmosphere. Now, when we look at the cosmic web, instead of seeing a web of galaxies and galaxy clusters merging to form large masses, we can now think of the cosmic web as the flow of space in our universe. We can see how space from large voids have been sucked up by mass and galaxies to form contributaries. These contributaries slowly merge to form streams. These streams continue to merge to form rivers, and these rivers all flow outwards to a central point or location, like rivers flowing out to the sea, where all the space of the universe, which is sucked into these central points. We can now see the cosmic web as the flow of space in our universe. If we think of space as a medium of particles, then what evidence would we look for to prove that space was not a vacuum, that space was a medium of particles? We would expect the particles in space to be moving, vibrating, to emit energy, to have a temperature, to have slight variations, just like the air in our atmosphere. We would expect it to be generally uniform with minor variations. If we were thinking of space as a medium, we would expect it to transmit waves like electromagnetic waves and gravitational waves. If we think of space as a medium of particles, this could be an alternative explanation for cosmic microwave background radiation. We would expect a medium of particles to have movement, vibrations, emit radiation, and temperature. Just like the air in our atmosphere, we would expect space to be grossly homogeneous throughout, with slight variations. All the properties that we observe in the cosmic microwave background radiation could be explained by the fact that space could be a medium. If we think of space as a medium like water, then we can think of gravity waves like ripples through space. If we think of space as a medium, then we could compare gravity waves to seismic waves or blast waves from a collision. Let's change tack for a minute. Let's talk about dark energy and the mass distribution of the universe. When I was a child, I could not understand why we did not know where the center of the universe was. In my mind, I believed that the universe was once much, much smaller, that over billions of years the universe has been expanding and consistently getting bigger. In my mind, I thought if the universe was much smaller and is consistently getting larger, then it must be expanding from a central point. If we were in the universe and we looked in any direction, we would see that towards the center of the universe, mass would be denser and closer together, moving slower. If we looked in the opposite direction, away from the center of the universe, we would expect that mass would be further apart, more vastly spaced, moving faster away. I could not understand why we did not know where the center of the universe was. Then I heard a theory that perhaps all the mass of the universe was heading outwards at exactly the same velocity. If this was the case, then all the mass of the universe would form a rapidly expanding sphere. We would expect that any mass surrounding us would be moving away from us relative to how far away it was to us. We would expect that the mass in any direction would be evenly distributed around us. However, if all the mass of the universe was on a single flat or slightly curved plane, then we would expect there to be no mass or a large void in the center of the universe and on the outside of the universe, and this is not the case. When we look at the universe, it looks a little bit more like this. From any point in the universe, all mass seems to be relatively evenly distributed. All mass seems to be moving away from us relatively equally, depending on how far away it is relative to us. This left me with these questions. Why is the mass-energy distribution of the universe the same in every direction? Why do galaxies move apart equally in all directions, proportional to their distance from us? Why is the universe expanding at an accelerated rate? What is dark energy? And how is it possible for the mass-energy distribution to stay homogeneous as the universe? I then asked myself, what else is evenly distributed while it expands? We all know of the analogy of the raisin bread, and we can compare raisins in the dough as galaxies in our universe. And as the dough expands and our universe expands, the raisins and galaxies move apart proportionate to each other relative to their given location. But what else expands evenly? When I was learning physiology, I learned about the properties of a gas. I found out that particles in a gas are moving around rapidly and will diffuse throughout their given volume. If we look at the distribution of mass in any volume of gas, it will be evenly distributed throughout its given volume. As that volume expands or contracts, the movement of those particles will continue to diffuse, and that gas will remain homogeneous and evenly distributed throughout. This made me think, what if space behaved like a gas? If space in our universe was like the air in a balloon, then we could imagine that the space in our universe would be evenly distributed throughout the volume of the universe. If the volume of the universe changed, the space in that universe would redistribute and remain equally. If we looked at a compressed gas, then all the particles are evenly distributed throughout the volume. If the volume increases, then the particles redistribute and remain evenly distributed. If we release the gas under pressure, then it expands due to a pressure gradient between the inside and outside of the gas until it reaches a new equilibrium, while the particles remain evenly distributed throughout its volume. What if the universe was like a volume of gas? If space was a medium which behaved like a gas, then space would be distributed evenly throughout the universe. Any mass in space, like galaxies, would be evenly or randomly distributed throughout the universe. As the universe expands, the space in the universe would remain evenly distributed, and any mass floating in space would also remain evenly distributed as that space expanded. If we look at the air inside a balloon, we can see that the mass is evenly distributed throughout the volume of the balloon. If we look at the air outside the balloon at 1 atmospheric pressure, we can see that that air is also evenly distributed throughout the atmosphere. Even though both are evenly distributed, there is a pressure gradient between the inside of the balloon and the outside of the balloon, which creates an outward force on the balloon. If our balloon pops, then the densely packed gas or air inside the balloon would redistribute outwards due to a pressure gradient as it tried to reach a new equilibrium with the atmosphere around that balloon. We can think of our universe in the same way. If our universe was a single mass of space, and the mass and space in our universe was equally distributed, and there was space outside our universe, which was at a lower pressure gradient than the space inside our universe, then we would have a pressure gradient between the inside and outside of our universe. There would be an active force causing the universe to expand outwards as the space inside our universe tried to redistribute and form a new equilibrium with the space outside our universe. If this was the case, then space and mass would be evenly distributed throughout the volume of the universe. There would be a pressure gradient between the inside and outside of our universe. This would cause the universe to expand at an accelerating rate. The space inside the universe would redistribute and remain evenly distributed throughout. Therefore, all the mass in the universe floating in space would remain evenly distributed as the universe expands. If there was a true vacuum outside of our universe, then the pressure gradient of the universe, the pressure outside our universe would be zero, and there would always be a pressure gradient between the positive pressure inside our universe and no pressure outside our universe. Therefore, the acceleration would decrease as the pressure gradient decreased, but the pressure gradient would never reach zero. There would always be a pressure gradient, and therefore there would always be an outward force acting on our universe, and the expansion of our universe would continue to accelerate indefinitely. Therefore, if space was a gas and the universe was a single mass of space, this would account for why the mass of the universe is evenly distributed, why the universe is expanding, why the expansion is accelerating, and why the mass of the universe remains evenly distributed as the volume is constantly changing. So let's summarize. Here's our hypothesis. 1. Space is a medium of particles which has properties similar to a gas. 2. Most objects in space are suspended, motionless, in moving space. 3. Mass constantly consumes space. 4. The effects of gravity are the results of the movement of space. 5. The gravitational acceleration is equal to the velocity and direction of space at any given point. And 6. The universe is a single finite mass of space. These hypotheses could therefore account for the effects of gravity, the natural occurrence of stable orbits in nature, the formation of galaxies, the observations seen around galaxy clusters and collisions, cosmic web, cosmic microwave background radiation, gravitational waves, the distribution of mass in the universe over time, and dark energy. So where's the maps? If we want to know about the flow of space, then we can compare this to the flow of water in a pipe. If we want to know the velocity and direction of movement of water at any given point, then we need to know the flow of water, the amount of water that passes past a certain point at any given time, and we need to know the surface area through which that water flows. If we know the flow and the surface area, we can calculate the velocity and direction of that water at any given point. If we state that gravity is equal to the movement and direction of space at any given point, then to calculate gravity at any given point, we need to know the movement and direction of space at that point. We can calculate the force of gravity as the flow, the volume of water consumed by the central mass, divided by the area, which is the surface area through which that space must travel through to reach that mass. We can therefore say that gravity, or gravitational acceleration, must equal the flow of space divided by the surface area through which that space must flow. So what is the flow of space? The flow of space is equal to the volume of space consumed by a mass per second. If mass consumes space at a constant rate, then we can create a new variable, Vx. Vx is equal to the volume of space consumed per kilogram per second. We can then calculate the flow of space as equal to the volume of space consumed per kilogram per second multiplied by the mass in kilograms. What is the area? The area is the surface area that space must pass through in order to reach that mass. If a single mass is consumed equally in all directions, then we can calculate the area as the surface area of a sphere. The surface area of a sphere is equal to 4 pi r squared. We can now take our formula for gravity, where gravity equals the flow divided by the surface area through which that space must flow, where flow equals the volume of space consumed per kilogram per second times the mass, where area equals the surface area of a sphere, 4 pi r squared, and therefore we can come up with a formula where gravity equals Vxm divided by 4 pi r squared. So we can say that gravity is equal to the flow of space divided by the surface area through which that space must pass. We can say that gravity is equal to Vxm divided by 4 pi r squared. We can say that gravity is proportional to the mass divided by the surface area. If the mass increases, gravity increases. If the mass decreases, gravity decreases. If the surface area increases, gravity decreases. If the surface area decreases, then gravity increases. This gives us the formula gravity is equal to the flow of space divided by the surface area it passes through, or gravity equals Vxm divided by 4 pi r squared. What is Vx? What is the volume of space consumed per kilogram per second? Well, we can take our formula and rearrange it. We already know the mass, gravity, and radius of most objects in our solar system. So we can take the objects in our solar system, their mass, their gravitational acceleration, and their radius, and we can use this to calculate the volume of space consumed per second per kilogram. And this equals around about 8.4 times 10 to the negative 10 meters cubed per kilogram per second. We can also derive Vx from Newton's formula for gravity. Newton's formula for gravity says that the force of gravity is equal to the gravitational constant times the mass divided by r squared. Our formula for gravity is that the force of gravity is equal to Vx times mass divided by 4 pi r squared. If we combine these two equations, we can see that Vx is equal to 4 pi gravitational constant. Therefore, we can say that the gravitational constant is the proportion of the volume of space consumed per kilogram per second. And we can therefore calculate Vx as equal to 8.39 times 10 to the negative 10 meters cubed per kilogram per second. Galaxies. Our current understanding of gravity does not account for the observed orbital velocity of galaxies. When we look at the orbital velocities of galaxies, they are far faster than what we would expect when calculating the orbital velocity given our current understanding of gravity. When I first came up with my theory for gravity and the calculations for gravity, I did not know about the galaxy rotation curve problem. When I found out about the galaxy rotation curve problem, I wondered, could my theory help answer the unexplained observed galaxy rotation curve? I hypothesized that the surface area through which space flows around a galaxy could be approximated by the shape of that galaxy. So if we have a single isolated mass, then we would expect the flow of space to be equal in all directions, and we can calculate the surface area through which space flows as the surface area of a sphere. If we see a circular disk-shaped galaxy, we could predict that the flow of space is proportional to the shape of that galaxy, and therefore we could calculate the surface area of the flow of space into that galaxy as the surface area of a disk. As a very wise man once told me, not all galaxies are flat circular disks. Galaxies come in all sorts of types. If we think of gravity as the flow of space and as mass flowing in that space, then we can use the shape of galaxies to predict the flow of space. We could predict that the flow of space in a spiral galaxy may be distributed in the shape of a spiral or a circular disk. We could expect an elliptical galaxy to have flow of space distributed in the shape of an ellipse. A regular galaxy to have an irregular flow of space. With simplicity, we could say that the flow of space around a galaxy could be in the shape of a circular disk. To generalize, we could then say that our formula, gravity equals the flow of space divided by the surface area through which that space travels through, could be Vxm divided by the surface area of a disk. If we take our new formula and say that gravity is equal to the flow of space divided by the surface area through which that space must pass through, and we say that the surface area of space in a galaxy is a circular disk, then we can take our new formula and predict the force of gravity using that calculation and can compare that to the force of gravity observed. And for this galaxy, we can see that our calculated force of gravity is very close to our observed force of gravity. We can do this for multiple galaxies, and again, we can see that the observed force of gravity is close to our calculated force of gravity. But what about the orbital velocity? Orbital velocity can be calculated as the centripetal acceleration is equal to the gravitational acceleration. Therefore, we can take our formula for centripetal acceleration and our formula for gravitational acceleration and calculate the orbital velocity. And again, you can see that our new calculated orbital velocity is very similar to the observed orbital velocity. So we can calculate the orbital velocity of any point in any galaxy from the visible mass, but we can also rearrange our formula so that we can, if we have the orbital velocity of any object at any point in any galaxy, we can calculate the mass of that galaxy inside that point. Here's our new equation and formula for calculating the mass, visible mass, at any point inside any galaxy, given its observed orbital velocity. And again, you can see that using the observed orbital velocity, we can accurately calculate the mass inside many galaxies. Now that we've compensated for our discrepancy between the observed gravitational force at the outside of a galaxy and the calculated and expected force, gravitational force at the outside of a galaxy, we can now accurately predict and calculate for gravitational lensing, one of the sources of evidence for the existence of dark matter. But not all galaxies are circular disks. Galaxies come in all shapes and sizes, so let's use some other examples and see how these work for calculating the force of gravity, orbital velocity, and mass of galaxies in our universe. Let's start with black holes. A non-rotating black hole consumes space equally from all directions. Therefore, we can calculate the force of gravity around a black hole as equal to the surface area of a sphere. However, as the spin of a black hole increases, so too does its angular momentum. With increasing angular momentum, the distribution of space around a black hole changes, and we need to calculate the surface area of a rotating black hole using the surface area of a spheroid, proportional to its angular momentum. Why is this relevant? Well, many galaxies have a supermassive black hole in the center of their galaxy. Therefore, many galaxies do not have the surface distribution of space in the form of a flat disk. In fact, these 4 galaxies are all non-barred spiral galaxies. As you can see in the non-barred spiral galaxies, the distribution of space is in a disk-like distribution for the periphery, the outside of the galaxy in many cases, but the center of the galaxy, the distribution of space is more consistent with that of a spherical distribution, which transitions into a flat disk as we move outward from the center of the galaxy. Therefore, we need to adapt the surface area through which space is consumed according to galaxy morphology. For individual objects with low rotational angular momentum, the distribution of space is consumed equally from all directions in the shape of a sphere. For large galaxies rapidly spinning with high angular momentum, their distribution of space is more of that of a single plane. But galaxies are in a spectrum. They are all different, and so we need to take a spectrum or a balance between the two for each unique galaxy morphology, depending on how the distribution of space is consumed. Non-barred spiral galaxies, we could say that the center of the galaxy consumes space from all directions, similar to a sphere, and that the periphery of the galaxy consumes space on a single plane, similar to a disk. We could use 2 separate formulas to calculate the gravitational force. However, this is messy. Alternatively, we could take a compromise and say that the gravitational force, orbital velocity, and mass can be better approximated if we use the surface area of a spheroid, and in between. If we say that the surface area of space consumed by a galaxy is in the shape of a spheroid, then we can alter our equation accordingly. Now we look at our 4 non-barred spiral galaxies. We can see that by using the surface area of a spheroid, we can far more accurately predict the calculated force of gravity closer to the observed force of gravity. In fact, we can cheat. We can manually adjust the eccentricity to perfectly fit all points in all galaxies. All galaxies start with a high eccentricity, which reduces with distance from the center of the galaxy. Unfortunately, I haven't come up with a reliable equation that calculates the eccentricity for all points in all galaxies. But from what I can see, the larger the mass of the galaxy and the faster the rotation, and therefore the larger the angular momentum of that galaxy, the higher E. And so E is directly proportional to angular momentum for individual galaxies and for each point in individual galaxies. Let's summarize. We now have a formula for gravity, which explains gravity is and how it works, has no unknown constants or variables such as the gravitational constant, gives mathematically identical results to Newton's equations for classical gravity problems, can calculate the gravitational force, the mass of a galaxy, or the observed orbital velocity at any point in a galaxy with over 95% accuracy in over 60 different galaxies and over 700 data points tested, and can be refined further when accounting for the galaxy type, and also has the potential to solve the galaxy rotation curve problem. So if we hypothesized that space is a medium, that mass consumes space, and gravity is equal to the velocity and direction of space at any given point, then we can come up with an explanation of gravity which accounts for the natural formation of stable orbits in our universe, can explain the formation of galaxies, helps us understand galaxy clusters and collisions, solves the galaxy rotation curve problem, could explain the cosmic web, helps us understand gravitational waves, accounts for all the properties of cosmic microwave background radiation, accounts for the mass distribution of the observable universe over time, and provides a plausible explanation for dark energy. Using these simple foundational principles, we can come up with a basic framework for the universe, which is all interconnected and explains all observable phenomena in the universe. We can say that space is a medium of particles which behaves like a gas, that this accounts for the distribution of mass in our universe, and that can also account for the accelerated expansion of our universe and dark energy, as well as how the distribution of mass remains homogeneous throughout, even as the universe expands. It can account for all the features of the cosmic microwave background radiation. If we say that space is a medium and that gravity is the flow of space, then this can account for stable orbits, galaxy formations, galaxy collisions, and clusters. It can account for all the properties of the cosmic microwave background radiation and the flow of space in our universe as the cosmic web. We can also use our understanding of gravity to better understand galaxy rotation curves, gravitational lensing, galaxy collisions, and therefore many of the properties of dark matter. What we haven't talked about today is how our understanding of space can explain the properties of electromagnetic waves, quantum mechanics, relativistic effects, time, and black holes. So, as you can clearly see, I've probably gone insane. But I hope you found this conversation somewhat interesting. But unfortunately, we're out of time today. I haven't had a chance to talk about quantum gravity, which I really, really want to talk about. Unfortunately, I need much more time. It's a big topic on its own. Haven't also gone into any details about quantum mechanics, uncertainty principles. I really wanted to go into electromagnetic waves, and again, that's a whole can of worms, because once I start going into that and talking about light, then we need to start talking about relativity, relativistic effects, and then we can talk more about dark holes, so black holes and dark matter. But unfortunately, we're out of time today. If you're still here, then congratulations, you've made it to the end of my presentation. Thank you so much for listening. I really appreciate anyone that's taken the time to listen today. It means a lot to me. Thank you. Enjoy the rest of your day.